So first up, we've got Lucia Bellino. She is a third-year PhD candidate studying volatile cycling on early Mars through high-temperature petrologic processes such as magmatic degassing. She earned her bachelor's degree in geology at Rutgers University in 2021 under the supervision of Dr. Chengwang Sun. Lucia uses thermodynamics and experimental petrology to investigate the cycling of hydrogen, carbon, and sulfur from the interior of ancient Mars to its surface to better understand the planet's paleoclimate and potential habitability.
Thank you. I just want to thank the Center for Planetary Systems Habitability for providing you with funding that supported this research. Okay, maybe we'll go quicker. Oh. Okay. There's extensive evidence to suggest that liquid water was present on Mars about 3 to 4 billion years ago. And the evidence comes in the form of deltas, dendritic valley networks, sedimentary rocks, and hydrated minerals like clays that we've detected both remotely and in situ on Mars. But in order for Mars to have obtained temperatures warm enough for liquid water to have existed, it is hypothesized that Mars had a dense CO2-rich greenhouse gas atmosphere with minor constituents like H2S and SO2 that would have allowed sufficient greenhouse warming for liquid water to be stable. In particular, sulfur is expected to play a key role in modulating the early climate of Mars because of the widespread abundance of sedimentary sulfate deposits at the Martian surface, as well as the presence of substantial amounts of sulfide within igneous Martian meteorites. But there is this incongruence. You have oxidized sulfates, sedimentary sulfates, at the Martian surface, and then you have reduced sulfides within igneous Martian meteorites. And this same discrepancy is present for carbon as well, where you have oxidized carbonates at the Martian surface, but then you have graphite within igneous Martian meteorites. Now, volcanism is probably the primary mechanism that transported sulfur from the interior of Mars to its surface. And volcanism and sulfate deposition were both occurring about 3 to 4 billion years ago on early Mars, at the same time that fluvial processes were active. And so the primary goal of this project was to determine what the dominant sulfur species were that were degassed on early Mars in order to better understand the planet's early climate and its potential for habitability. Now, we're not the first study to investigate sulfur degassing on early Mars. This is a figure from a paper that came out about 15 years ago. On the y-axis, we have the SO2 to H2S ratio on a logarithmic scale. On the x-axis is the pressure of the Martian atmosphere in bars, or I guess just the pressure in bars on the x-axis. But I've drawn in 2 blue dashed lines here to show you where potential pressures for the Martian paleo atmosphere would lie, as well as a black dashed line to show you a 1-to-1 ratio of SO2 to H2S in the magmatic gas. And you can see that most of the scenarios fall above this 1-to-1 line, where more SO2 is degassed than H2S. But these previous studies neglected to consider several key magmatic processes. The first being sulfide and graphite saturation. And with sulfide and graphite both present in Martian meteorites, we assume that these are key processes that would have occurred within Martian magmas. They also do not look at magmatic differentiation, which I'll go further into in just a second. And then they also only look at sulfur solubility as a singular temperature, composition, and redox condition, as opposed to changing with an evolving magmatic system. Okay, and so let's go back to magmatic differentiation. So magmatic differentiation is just when you have the process of a magma crystallizing. And so when you have a magma crystallizing, you're going to concentrate incompatible elements in the residual melt. So those are the elements that don't want to go into the crystals, into the minerals that are crystallizing out, and they'd rather stay in the melt. And so those incompatible elements are going to become increasingly abundant in the residual melt as you have crystallization occur. So this is going to change the composition of things like magnesium, iron, calcium, sodium in the magma. But it also changes the redox condition of the metal. So iron 3+ is the more oxidized form of iron in comparison to iron 2+. But iron 3+ is more incompatible than iron 2+ in silicate minerals, so things like olivine, pyroxene. So when you have crystallization of silicate minerals, the melt is going to become more and more oxidized, the residual melt becomes more and more oxidized. But for oxide minerals, things like spinel, iron 3+ is more compatible, so it prefers to go into those oxide minerals, and iron 2+ prefers to stay in the melt. And so as you have crystallization of oxide minerals, the melt becomes, or the residual melt becomes increasingly more reduced. So it can affect the, it changes the redox state of the magma as you have differentiation. And the equation here shows the relationship between iron 2+ is FeO and iron 3+ is Fe2O3, and its relationship with oxygen. And something to come up throughout the talk a bit is oxygen fugacity. So to make sure that I took a sidebar to kind of explain what oxygen fugacity is. Oxygen fugacity is proportional to the partial pressure of oxygen in the system. And if I gave like the actual value for oxygen fugacity, sometimes written as FO2, it would be like 10 to the negative 20 something to 10 to like the negative 7, which is really hard to understand. It's a super small number, hard to understand how things are changing or compare different systems. So as opposed to actually giving you the value of like FO2, we give you it relative to a mineral buffer. So for this one that we'll be using, it's the phthalate magnetic quartz mineral buffer, or FMQ. And it's actually like the equilibrium reaction between phthalate, which is the iron-rich end member of olivine, oxygen, and then magnetite and quartz. So if you had these three phases coexisting at equilibrium, you'd be right at the FMQ mineral buffer. And this is like somewhere near where we assume the terrestrial mantle to be. But the Martian mantle is more reduced, Martian magmas are more reduced than those on Earth. And so we give it relative, we give their oxygen fugacities, the redox conditions, relative to the FMQ mineral buffer. So the more negative value we have, the more reduced the system is. The most reduced system that we'll be looking at today is at 3.7 log units below the FMQ mineral buffer. And the most oxidized system we'll be looking at is only 1.3 log units below the mineral buffer. So less negative is more oxidized, more negative is more reduced. Okay, now going back to magmatic differentiation. The other important part is that this concentration of incompatible elements in the residual melt also means that volatiles are going to concentrate within the residual melt. So carbon, hydrogen, and sulfur species will become increasingly abundant in the residual melt as you have crystallization occur. And we see this present within Martian meteorites. So over here, I have a figure that shows the redox condition of Martian meteorites relative to the FMQ mineral buffer. On the x-axis of temperature. As temperature decreases, you have crystallization increase. You can see a general trend of increasing oxidation state with increasing extent of crystallization. And then over here on the right, I have the sulfur content of Martian meteorites on the y-axis, and then the MgO content on the x-axis. And so as MgO decreases, crystallization increases. You can see a general trend with crystallization increasing, that you have an increased amount of sulfur in the melt as well. Beyond just the redox state and the volatile compositions, there's also significant amounts of compositional variation within Martian meteorites. So these plots show both Martian meteorites, or these red dots, and then Grover data for all of the other points on these plots. And all of these have MgO content on the x-axis. So again, as MgO content decreases, crystallization increases. And you can see that other components of the melt, like SiO2, CaO, Al2O3, and FeOT, change depending on the extent of crystallization, and there's quite a bit of variation. And so that means it's really important to consider magmatic differentiation as we model magmatic systems on Mars. Also, it's important to note that we don't actually have any pre-degassed volatile contents for Martian meteorites or Martian magmas. So even that plot I just showed you of sulfur in Martian meteorites are already for degassed magmas. None of them are like the pre-degassed contents. So we select two different compositions in order to start modeling magmatic differentiation. One is a depleted composition and one is an enriched composition to represent two different primary magmas. So these are magmas that formed from a depleted source in the mantle and an enriched source in the mantle. We then conducted petrologic modeling with a tool called rhyolite melts in order to model the liquid lines of descent of each of these primary melts. Liquid line of descent just shows how the composition would change as you had crystallization occur. For our enriched primary composition, we selected Northwest Africa 1068, a meteorite, in order to represent the primary composition. You can see its liquid line of descent in purple here, and the Los Angeles basaltic sugarite falls on this liquid line of descent as its evolved counterpart. So we have the primary enriched composition is NWA 1068, and the evolved enriched composition is Los Angeles basaltic sugarite. And the same thing, we did the same thing for the depleted composition. So we had Yamato 980459 as the meteorite that represented our depleted primitive magma. And then Queen Alexandria Range 94201 or QUE 94201 represents the evolved depleted composition. And both of these series also follow the expected redox trend, where you see that the more evolved melt is more oxidized in comparison to its primary counterpart. We then are able to use the melt compositions to estimate the temperatures of these magmas and then determine the extent of crystallization. So the two primary magmas are ones that have not experienced any crystallization, so they are 100% liquid. But QUE 94201 experienced about 55% crystallization, while Los Angeles experienced about 70% crystallization. We then assumed a fixed value for the water content and the sulfur content of the Martian mantle, because there aren't any rigorous constraints on what those mantle values are. So they're kind of just the average of the literature review that we conducted. And then assume 10% partial melting to produce these magmas, and then the crystallization. The only one that's different is carbon, because there is a different study that parameterized carbon content in primary melts from a graphite saturated mantle. And so we used that parameterization to calculate the carbon content of the primary melt of Yamato 90459, and then just adjusted that for the two evolved melts with crystallization. So that's kind of how we modeled magmatic differentiation. But in order to model magmatic degassing, we used the magma and gas equilibrium calculator, or MAGIC, which is a MATLAB and Excel-based program that is able to determine the H2S volatile concentrations in the melt and in the vapor, with the H2S volatile solubilities as buffered by a series of redox reactions. And it's also unique in its consideration of graphite and sulfide saturation, which is the first degassing program that can do so. And it's also been recently updated with a new iron and sulfur redox model that makes it appropriate to use for Martian magmas. Here are results just for one of the magmas, and I know that these plots can look overwhelming. So I'll try to go through them slowly. On the y-axis here, we have pressure in bars on a logarithmic scale. Anything less than 1 bar is pressures that are potentially relevant to the Martian paleo-atmosphere. On the left here, we have the volatile species that are dissolved in the melt, also on a logarithmic scale. And so you can see that at both crustal and atmospheric pressures, S2- is the dominant species dissolved in the melt, and H2O is the second most abundant species dissolved in the melt. We can also see that there's an increase in reduced species like CH4 and H2 associated with graphite saturation. And then that sulfide saturation is maintained from initial degassing all the way to surface conditions, and is associated with an increase in oxidized species like S6+. Perhaps more interestingly, if we move to what the volatile species look like in the vapor, you can see pressure again on the y-axis, and again, anything less than about 1 bar are pressure potentially relevant to the Martian paleo-atmosphere, and then the concentrations of the volatiles in the vapor on a logarithmic scale on the x-axis. At crustal pressures, we can see that carbon species are more abundant, so that green line is CO2, and that like brown dashed line is CO, and those are dominantly degassed at crustal pressures. Whereas at surface pressures, hydrogen species like H2O, that blue line, and H2, that like teal dash line, become prominently degassed. But perhaps most interestingly is the sulfur speciation. At surface conditions, you can see that the pink line, S2, is actually the most abundant sulfur species degassed at Martian surface pressures. And H2S, this orange line, is the second most abundant sulfur species degassed at surface conditions. It appears that SO2, that red line, is the least abundant sulfur species degassed at Martian surface pressures. So we're just gonna zoom in on the sulfur species now. This is just for the two depleted magmas. So as a reminder, the blue line Yamato is our more primary depleted composition, whereas QE 94201 is our evolved depleted composition. On the X or the Y-axis for all three plots is pressure in bars, and anything less than 1 bar is still potentially relevant to the Martian paleo atmosphere. And in panel A here, we have the redox condition as delta FMQ. You can see that the primary magma composition doesn't change a lot. Its redoxity doesn't change a lot at different pressures, but QE 94201, the evolved melt, has a sharp decrease in its oxygen degassity associated with graphite saturation, and then an increase in its FO2 with sulfide saturation. And I should say that you don't see this for the primary magma because it never obtains sulfide or graphite saturation. And panel B is the SO2 to H2S ratio of the magmatic gases. And you can see that these two, they both increase as the pressure decreases, and this is per a pressure effect with the equilibrium reaction written here. So as you have lower pressures, you're going to proceed to the right side of this equation and degas more SO2. In panel C, we have the S2 to H2S ratio of the magmatic gases. And you can see that again, it increases as pressure decreases per a pressure effect on this equilibrium reaction. But for SO2 to H2S, we never surpass a 1-to-1 ratio. So there's always more H2S being degassed than SO2. But for S2 to H2S, you can see a crossover somewhere around 1 bar, such that S2 becomes the dominant sulfur species degassed on early Mars. If we add the two enriched series, or the two melts from the enriched series on this as well, you can see that the trends are generally pretty similar. The primary melt does not obtain graphite or sulfide saturation, and so it doesn't have large variations in its oxidative fugacity. But the Los Angeles basaltic sugar type B evolved composition reaches graphite saturation upon initial degassing as well, and then also sulfide saturation from initial degassing to surface conditions, and then becomes increasingly oxidized in association with the sulfide saturation. We can see that the SO2 to H2S ratio again increases and can slightly surpass the 1-to-1 ratio here. But even so, it's like an SO2 to H2S ratio of like 1.2. And in those cases, there's far more S2 that's being degassed than SO2. And most of these magmas still have this crossover around 1 bar. And all of them have S2 as the dominant sulfur species degassed at Martian paleoatmospheric pressures. So if we combine all of this into a comprehensive sulfur cycling model for Mars, we propose that primary melts are graphite and sulfide undersaturated. But as crystallization occurs, the incompatible carbon and sulfur volatile species become increasingly concentrated in the melt, in the residual melt. And then through this crystallization, evolved magmas are able to reach sulfide and graphite saturation, indicating that the Martian crust could be an important reservoir of carbon and sulfur. As for magmatic degassing, S2 is the most abundant sulfur species degassed by Martian magmatism, with H2S generally as the second most abundant species, or sulfur species. In order to reconcile this reduced sulfur degassing with the sulfate deposits we see throughout the Martian surface, we proposed that there was a secondary oxidative weathering mechanism. And so we proposed that there was hydrologic weathering. So I should say that S2 would precipitate into elemental sulfur, which could then experience hydrologic weathering alongside the basaltic Martian crust in order to produce the hydrated sulfates that we observe widely throughout the Martian surface today. And kind of taking things further, and also outside of my comfort zone, so we're just kind of speculating here that potentially H2S and S2 could have contributed to a thick, hazy atmosphere on early Mars. S2 can be polymerized into S8, which is an aerosol that can contribute to haze formation. And recent studies on exoplanet atmospheres indicate that even trace amounts of H2S can lead to larger particle sizes and thicker hazy atmospheres on exoplanets and in CO2-rich atmospheres. And Mars also would have had a CO2-rich atmosphere, so potentially H2S could have been a driver to produce a thicker, hazy atmosphere. And although the exact climatic implication of a hazy atmosphere isn't quite clear, one potential possibility is that Mars is a very halogen-rich planet and likely would have degassed substantial amounts of fluorine gas. And S8 could react with fluorine gas to produce SF6. SF6 is a super potent greenhouse gas. It's 20,000 times stronger than CO2. So that could be one potential avenue through which this Martian paleoclimate was affected by this hazy atmosphere. Although the exact climate implications are still unclear. And finally, it was just interesting as we did this project, as we kind of gotten the results last summer, the Curiosity rover accidentally crushed a rock, and within the rock was elemental sulfur, which kind of supports a lot of our results here. So I'll just leave my conclusions up, and I'm happy to take any questions. Thank you.
We have a couple of minutes for questions, and I'll also monitor the chat online. Yeah, cheers online.
Wow.
All right, well, if we have no questions, thank you very much.
Thank you.
Ryan, I saw you unmuted. Were you about to ask one?
Oh yeah, I was gonna just ask, that was kind of fortuitous that that instrument broke the rock. Was there not an effort to break it?
No, I don't think so. I think that it just accidentally rolled over one, and it happened to crack. So it was kind of just like a fortuitous discovery.
Nice.
Tim, looks like you're raising your hand.
Yeah, sorry, I was trying to find the new Zoom raise hand, but Lucia, I was wondering if you have any sense of like the timescales of alteration to go from elemental sulfur to sulfate, to hydrated sulfate, just to think about when elemental sulfur might have been deposited compared to the deposits we find it in are mostly Hesperian in age, but like what are the time, or if you've thought about what the timescales of alteration are?
Yeah, I haven't thought about that much, and I think that would be something that would be really interesting and important to look into further. But to the best of my understanding, the elemental sulfur would be much less stable at the Martian surface than sulfate would be. And so I expected it to be pretty quick, but as far as actual timeline, I haven't looked into, and I should do that. So thank you.
Great, thanks.
All right, thank you. Neel, if you could go ahead and start sharing your slides.
Yeah, sure. Just gonna do that. Share screen. Okay, let's look for the slide. Okay. All right, sure. Shall I begin?
I'll introduce you and then you can get started. All right, Neel Nagarajan is a first-year astronomy PhD student at UCLA, currently working with Dr. Brad Hansen in exoplanetary orbital mechanics. He graduated from UT in May 2023 with a Bachelor of Science in Astronomy and Physics here, where he conducted the work that he's going to present related to CPSH. He currently continues to pursue his passions for astronomy through the PhD program and loves to connect with other individuals on topics related to astronomy.
Yeah, thank you for the introduction. So yeah, I guess I still kind of graduated fairly recently, and the work that I'll essentially be presenting right now is what I did in the at least a few months up to maybe year after that until I got into grad school. So I was able to work on this for a few months, and yeah, kind of recently, I guess I left UT. Otherwise, I would have loved to give this presentation in person, but nevertheless, it's great to be able to give it online. So yeah, I'll introduce. This is what I was able to work on for a few months with Dr. William Cochran. So our goal was essentially to simulate the interior structure and thermal evolution of a certain type of Earth-like exoplanet. So a little bit more background. So how do I go? Okay, there we go. Second slide. So A little bit of background is that we were interested in, so for planets that, Earth-like planets that formed relatively early in the universe, so we're looking at planets that would have, for example, if they were sort of like Earth, but they formed earlier in the universe, then they would have just, for example, had like lower metallicities and different core to mantle mass ratios, etc. But we're interested in whether they could have at any time been habitable to life? And if that is the case, then how long, if at all, could they have sustained habitable conditions? Because we do know that, like, so these planets, I mean, if they could have sustained life for a consistent amount of time, they would probably have the best shot of hosting life, even intelligent life. And so we're interested in seeing if these planets could have been habitable at all, and maybe even over a period of time. Maybe a bit of a larger backstory, and okay, I know this might be a slightly debated point, but at least some scientists, I think, in the field think that we are sort of we're able to advance observations forward with time, like we're launching, building more telescopes like JWST and the Giant Magellan Telescope, etc. We are going to be able to keep getting more data from exoplanets, but at the same time, we need to ensure that we're able to also develop stronger theoretical models or theoretical understandings of how these planets work and how they evolve in order to be able to interpret observations that might come our way in the future. So this is essentially driving this whole, I believe some people at least call this field exogeoscience, the studying the evolution and dynamics of other planets. And there are a bunch of different codes and models that are being produced for simulating various aspects of exoplanetary evolutions. That includes the thermal/interiors, includes the atmosphere, etc. Some of us, like what I'm actually about to describe very shortly, even want to be able to build sort of like one master simulator that's capable of simulating like a lot of different physical phenomena and a lot of different factors at once in determining the long-term evolution of an exoplanet. And yeah, collectively, this has, of course, led to multidisciplinary collaborations like CPSH. So yeah, I'll talk about vPlanet a little bit. That's actually the software that I used for the most part. It is developed by VPL Labs in the University of Washington, primarily headed by Dr. Rory Barnes. Essentially, the way it's being designed is that it has a bunch of different modules. Each module can simulate a specific ingredient of the physics or a specific factor. So, for example, when you're simulating the evolution of an exoplanet, one module or one factor would be for simulating the host star, which is, of course, nearby. And then, how does that evolve with time? How's that going to change? And then a bunch of other factors as well. So the whole idea is that it's very like I guess discretized or like different modules for very specific purposes. And the key thing is that it's possible to add and subtract physics very easily. So if you want to understand the effect of a certain module or physics effect on the evolution of a planet, it's possible to say run the simulation without that particular module, and then add that module or add that physics and then run the simulation again. So it's very easy to add and subtract modules or add and subtract physics, and that's sort of what, at least I like to sort of think of it as like a master simulator. So I will say a little bit more on this, but I want to sort of clarify ahead of time that this is what they're building towards. It's very much in progress right now. So right now it's probably not quite at that stage where it can do that very easily, but it's definitely something that they are working towards. But so onto our strategies. So once again, we're trying to replicate and simulate planets that are probably Earth-like, but formed earlier in the universe. So there are a number of things that would be slightly different for these planets. The main one is going to be the core to mantle mass ratio, which is a consequence of the composition that went into producing these planets. So if these planets were produced earlier in the universe, then they would have a lower overall metallicity at least, so probably less iron, nickel, etc. they would have larger quantities of radioactive elements, which tend to go into the mantle of the planet. And collectively, yeah, this tends to result in planets that have lower core to mantle mass ratios than, say, in the case of the Earth. So essentially, the core is going to be a bit smaller and the mantles are going to be larger. And also, as we'll see shortly, the planets overall, like for a given mass, actually tend to be larger when that is the case. So this is just a schematic of sort of just a visual of how, like, at least the vision of V-Planet is designed to work. You can very easily add and subtract bodies or planets from the system that you're simulating. You can add and subtract parameters and processes. So that's how it's designed to be incredibly user-friendly in that regard. And that's how it's meant to work. So we actually used sort of two software in conjunction. So, okay, the main one is vPlanet, but we did also use another one called Magmatic. Maybe some of you know and use it. We used it to develop instantaneous structures, instantaneous planetary structures that are, you basically input like different values for, okay, this is the mass of the core, the mass of the mantle, and then this is like the temperature at the boundaries, etc. You input some things like that, and you're able to develop an instantaneous structure of a certain planet. And then we were able to take parameters that are outputted by Margaret and input as many of those as possible into vPlanet. And then once we input them into vPlanet, we use two primary modules. One is called Thermint, which is designed for most of the physics that is involved with regards to simulating the interior thermal evolution of a planet. And an additional module called RadHeat, which allows us to play around with the initial quantities of radioactive elements that are inside these planets. And that is important because the radioactive elements are what produce at least a fraction, if not a lot of the energy, even the energy inside the Earth right now. Some of it is produced by radioactive elements. So they are very important in determining the thermal evolution of these exoplanets. The main species that we looked into are uranium-235, uranium-238, thorium-232, and potassium-40. And in the end, we kind of decided to mostly stick with a planet mass of 1 Earth mass and focus on playing around with core to mantle mass ratios along with quantities of radioactive elements, and see what the evolutions of the temperatures and a bunch of other things inside these planets look like. So we're going to look at that now. So what I'm plotting over here, it's actually 4 different plots. They're all plots of the radiative power produced by the mantle of the simulated planet as a function of time. So if I actually recall correctly, currently the simulation, I believe it was capped at 8 billion years. So that's why all these simulations are 8 billion years long. But what I've essentially done is I've taken the quantities of these 4 species, so 235, 238, 232, and the 40. So I've taken those 4 species and I've played around with how much am I inputting of those into each planet. So, for example, in the top left planet, I believe that was the one where I took the uranium-235 and I took its total quantity, the amount that it is present in the Earth, and just multiply that by a factor of 10. So essentially what that does is it ensures that the heat production inside the mantle is primarily dominated by that particular species. So in the case of the top left, it was U35, so you can see what the decay trend looks like. And then for the one to the right, I believe that one was for that one, I took the U38 and multiplied that the quantity of that species by a factor of 10 while keeping all the other species to Earth-like quantities. And in the bottom left, I believe that one was thorium-232, and bottom right, I believe, was potassium-40. So I actually should have probably labeled each one of them with which species I was altering. But essentially, in all of these, the difference is that I've taken one of the species and I have times 10 that particular species, and all other species were kept to the same quantity as what is what was initially present in the Earth. And the key difference that we're able to observe is that the decay trends of the power produced in the mantle as a function of time are a little bit different. And some they're a little bit steeper or quicker, and in some they take a little bit more time. Essentially, it's just dependent on the half-life or decay time of the radioactive species that is dominant in that particular planet. So this is sort of like a sanity check, but we were like able to see that the generally expected decay trends depending on which radioactive species we set to be dominant in that particular planet. So, and yeah, on the color axis, we in this case, we're playing with the core fraction, which is the quantity of the planet's mass that is present in the core. So I will say one thing that I think, as I mentioned, vPlanet is something that is currently in progress, and it can't quite, I would say, execute their final vision, which is to be able to build and simulate any planet in any system. And what I essentially mean by that is because it's something that is currently in progress and being developed, a lot of vPlanet's internal source code, so that includes a lot of Earth constants, a lot of routines, etc. A lot of them are, a lot of the Earth constants are, I would say, hardwired at multiple locations in the code, and it's understandable in that the purpose of that is to ensure that, okay, if they're like building models and building simulations, they probably want to ensure that, okay, this works for the Earth first before we're able to confidently extrapolate that to other planets. So it is in that phase right now. I think a number of results that we have been able to produce are probably not immediately reliable, in that a lot of them would probably look a little bit different if we were able to sort of simulate other planets from scratch without there being some dependence on Earth constants, etc. Another detail right now is that we wanted to be able to essentially just play mix and match with all the different modules, right? Each module adds a different type of physics or a different factor. We wanted to play mix and match and just like try all these different combinations of modules to see what the results look like. But right now, that wasn't quite possible, in that because these are also in a testing phase, they're kind of currently designed to work together in very specific combinations. So one example is thermant and rad heat, which is designed for interior Earth evolution. So that's also something else. I think the mix and match, the ability to run almost any combination of modules together, as long as those are, of course, producing physical results, is probably something that's still being worked on. But I would say that essentially we've built a framework. We've built the ability to, with one click, run Magrathea and run vPlanet, that essentially runs these simulations and output like a bunch of different quantities. So I think over here we did power produced by the mantle, but there are, I think, like 50 plus other quantities that we're able to easily plot their evolution as a function of time. It's just that, okay, once we're actually able to work with like other planets from scratch and sort of like leave that dependence on the Earth, then those results would probably be a little bit more reliable. But yeah, we definitely have a framework down right now to, I would say, execute that when the right time comes. So another interesting thing we noticed is that so when we're simulating planets, of course, the main thing that we wanted to vary is the core to mantle mass ratios. And essentially I would say, okay, so for any one planet mass, having different core to mantle mass ratios actually produces, due to like the densities involved, etc., it actually produces planets with different radii. So you can kind of see over here how I have basically plotted radius as a function of mass. And each color basically represents a slightly different core to mantle mass ratio. And you can see that the trends are slightly different depending on the core to mantle mass ratio. So the slight challenge, I guess, we had to figure our way around there is that for any one given mass that we wanted to simulate, there were multiple different core to mantle mass ratio. So that's just an area where, for example, I had to sort of try to use Python, I would say array indexing cleverly to be able to accommodate all of these different combinations and different radius values for any given mass. And this is a similar result produced by Dr. Cochran, I think, using a different code, but it also shows that the radius trend varies strongly as a function of the core to mantle mass ratio. So yeah, I guess this is a sort of maybe approaching a summary time, but this is essentially what we've been able to build. We're able to plot like a lot of temperatures. So this is temperature of the mantle as a function of the time for different core fractions. This is a temperature of the mantle as a function of time, where I'm varying the mass of the planet, all other things held constant. So we're essentially, and there are like 50 or so other quantities that we're able to plot as a function of time pretty easily. So of course, I'm like not quite able to show all of those evolutions over here. But we are essentially able to do this very easily, where we kind of vary any one parameter at a given time. So when I'm varying one parameter, it's like, okay, all other parameters are essentially being held constant. So I think what I would like to implement in the future, once it's the right time, is the ability to do a model grid. What that basically means is not just vary one parameter at a time, be able to vary a lot of these different parameters at one time. That'll, of course, probably produce a huge number of simulations and a huge number of plots. But then again, I think to be able to identify what are the most statistically significant trends as certain parameters change. I think that would be very interesting. And there are also other codes being developed. Maybe all of them are probably not, I would say, master, like designed to like simulate like a lot of different physical processes at once, but there are definitely other codes that are strongly focused on interior thermal evolution that are making good strides towards being able to be implemented for like any planet. Like you can build any planet from scratch and simulate that planet's interior thermal evolution. So some examples are Dr. Brad Foley's code. He is in Penn State. Dr. Doug Hemingway's code in MATLAB, I believe he's in the audience. And yeah, that's probably about it. So we definitely have a framework of down right now. And personally, yes, I'm very excited to be able to implement this once maybe V planet's at like a slightly later stage in its evolution. So yeah, I think it's probably all I had. Yeah.
Any questions in the room? All right, are there any questions online? We'll give folks a moment to unmute and or raise their hands. Oh, we've got one in the room, yeah.
This might be a little simple, so I apologize, but when you were talking about the simulations for like uranium and thorium, what was the, and I might have just missed this, but what was the reasoning behind the multiplying by 10, like in comparison to realistic values of other elements on Earth in your simulation?
Yeah, so that was sort of just experiment to, I would say, verify that we were able to reproduce the expected results. So we kind of purposely made one species dominant at a given time, and we wanted to verify that, okay, because that particular species has a certain decay time or decay trend, essentially the decay trends of the total energy produced in the mantle were sort of responding appropriately. So if I have a species that if the dominant species is something that decays very quickly, then I would want to see like a relatively quick decay trend in the total power produced by the mantle, and vice versa. So it was sort of a, I guess, like sanity check sort of thing. It was just sort of like experimenting and verifying that the like simulations are giving out the expected trends. And yeah, it was probably just in the spirit of experimenting. I mean, one of the things I enjoy about simulations is the ability that to just try anything out, and the worst that happens is the code doesn't work, I guess. So
Yeah, thank you so much.
no worries. Yeah.
Brandon.
Oh, yeah.
So Neel, it's great to have all these different kinds of physics, but if you have enough different types of physics, you need to constrain it by data, and the data on the exoplanets is not very good, so at what point will you have enough data to be able to constrain these models?
That's a good question. I don't know exactly for sure, but it was sort of like a general, I would say futuristic statement based on like what we're kind of building in the years to come. So yeah, we don't have that much more of an answer on that, but I believe that it's a view shared by at least some people, I suppose. So.
All right, well, thank you very much, Neel. For everyone, thank you for attending. We will have our next talk on February 10th, where we will have a postdoc associated with the OSIRIS-REx program and some of their sample analyses. So hope to see you then.